Thank you for your introduction. My name is Zhenyi Wang, and I'm an assistant professor in the Department of Computer Science at the Institute of Artificial Intelligence. And so my research focuses on continual learning, data efficient learning, and trustworthy AI. These three areas are mutually beneficial for each other. For example, my research in continual learning will benefit trustworthy AI research, and also my research in continual learning also borrow ideas from trustworthy AI. So in today's presentation, I will mainly focus on continual learning research. So the continual learning is to focus on the machine learning in non-stationary data distribution. This is because in standard machine learning, they assume the machine learning happens in a stationary data distribution that will not change over time. But in reality, the situation is reversed. The data distribution always changes over time. It will balance new task learning and old task knowledge preservation. So in this presentation, I will present two orthogonal approach from a data perspective and model perspective. It is called data-centric approach and model-centric approach. For the data-centric approach, I will focus on to transform the data to mitigate catastrophic forgetting. And for the model-centric approach, I will focus on from the model parameter adaptation perspective. So in this line of research, I developed a theoretically novel and efficient framework. This enables the machine learning system to be adaptive for real-world application. And I also build connections between continual learning, robustness, and the foundation model. So I also published more than 15 papers in top-tier conference and journals. So by developing a theoretical framework, this will be helpful to develop an adaptive and efficient framework for continual learning. So now let's see what is continual learning. So continual learning is to improve the standard machine learning that only assume static data distribution. For example, in the first stage, suppose we train a machine learning model that only classifies a cat and bird. But after that, a new data set comes in, like the lion and the deer. So if we incrementally train the models on the lion and the deer data set, it will gradually forget the knowledge learned during the first stage. That is, the accuracies for predicting the cat and bird will decrease a lot. So this is also known as catastrophic forgetting. And this is a core problems that I will address in this line of research. Continual learning has many applications in real world. So first is the large language model fine-tuning. So for the large language model fine-tuning, it has several stages. The first stage is perform pre-training. We use lots of data set to pre-train a good foundation model. After that, we will perform instruction tuning to further fine-tune the pre-trained model. This will help the model to have instruction following capabilities. And after the second stage, it will perform alignment. This will help the models to achieve better alignment with humans' intention. For example, we can also for a safety alignment to make the model output safe content. However, there is a critical issue is that, for example, after we perform the pre-training and then we perform the instruction tuning, the pre-trained knowledge will be gradually forgotten. And similarly, after we perform instruction tuning and perform the alignment, then the knowledge learned during the instruction tuning and the pre-trained model will also be gradually forgotten. So to mitigate this forgetting, we can apply the continual learning techniques and concepts to mitigate the forgetting. The second application of continual learning is on-device learning. So in the on-device learning, we only have limited computation and memory resources. So we cannot store all the training data during the learning process. We have to discard many previously trained data set. and then learn on the new data set. So there is also like a catastrophic forgetting when the model adapted to the new data distribution. Then continual learning plays an important role to mitigate the catastrophic forgetting during these two scenarios. Now, I will discuss the first line of my research is about a data-centric approach to mitigate catastrophic forgetting. The first approach is called memory evolution. So for memory evolution is that, for example, suppose this is a small memory buffer that stores some like previously learned data set, and then we can replay this data set in the later stage to mitigate forgetting. Suppose this orange line represents the raw memory buffer data, and this blue line represents the data distributions of the entire past data set. So clearly there is a big gap because if we have all the previously learned data set, we will have no forgetting. So to mitigate this gap, and I propose like a memory evolution to reduce the gap between these two data distributions, so we can achieve like a better performance. So the second branch of my method is about memory compression. This approach is that for a raw memory data set, suppose this is a 2D image. If we simply like performs the learning on this 2D image, like for some like a very large image, like a high resolution data set, so it will consume a lot of memory storage. To reduce the storage, we propose like low rank decompositions by decompose this raw image data set into two low rank matrix multiplication as L and R. By decompose this image as two low rank matrix, because K is much smaller than M and N. So this will greatly reduce the number of the memory storage requirement compared to the raw image, and then we can store much more data set in the memory buffer. The second line of approach is called a model-centric approach. So model-centric approach, the first is I propose active forgetting, also known as beneficial forgetting. This is to simulate how the humans learns new knowledge. For example, for the human brain, like some researchers study that they actually like perform like some active forgetting. They will like gradually forget some irrelevant knowledge. Then they can have more space to learn the new knowledge, and then this will improve the plasticity during the learning process and gradually learn the new task data. The second approach is called parameter sensitivity reduction. The intuition behind this approach is that, for example, this blue line represents, suppose it represents the original continual learning curve, and this red line represents the no, this red line represents the original continual learning curve. This blue line represents the parameter sensitivity reduced learning curve. So if the parameter sensitivity is high, if we gradually change the data set, then the loss function will change very rapidly. But if we reduce the parameter sensitivity, if the data distribution change, the loss function still not increase a lot. So by reduce the parameter sensitivity, we can gradually mitigate the catastrophic forgetting. But this kind of like continual learning research mostly focus on like theoretical and simulated scenario. So to apply continual learning in the real world applications, there are still several challenges to be solved. For example, in the embodied AI scenario, like we want to empower the AI with like some real bodies, similar to the human learnings, like a human has a real body to like interact with the environment. So for the embodied AI, if we want to if we want to embody the AI agent to perform the learning task, there are multimodal signal. For example, there are maybe like a vision, language, and touch. So these kind of signals and how can we integrate this kind of different knowledge to mitigate the forgetting during the learning process. And also the second challenge is that for the embodied AI, the environment is not predefined in advance. So the environment itself is highly dynamic and there is no clear structure and boundary. So to perform continual learning, we have to gradually detect whether and when the environment change over time. The second is about the scalability and efficiency issue because for the embodied AI, such as the robotics, the drone, this kind of device, if we want to perform on-device learning, there is often limited computation and memory capacity. So we should develop more efficient adaptation strategy to achieve real-time response and adaptation. So for the future research, in the nearby 1 or 2 years, I would like to launch the projects in the embodied continual learning and then incorporate human feedback to interact with the environment. And for the long-term research goal, my research goal is to lead the advance in the continual learning for the embodied AI system and language agent. The second benefit is that because continual learning can mitigate the retraining, because when we have some new data set or task to learn, we don't need to retrain from scratch. So this is beneficial to achieve green AI. And I also would like to develop new courses and partner with some NSF, Mayo Clinic, and other partners. And also these research directions also align with the US and global priorities on the green AI and energy efficient learning. Thank you for listening.